3 properties down, 2 to go. So we'll pick up with where we left off in our list of ways definite integrals behave. So I mentioned previously that the first 3 properties that we saw, I think, are pretty intuitive. It's not that these aren't, but it can be a little bit trickier to get your head around them, in my experience, relative to the, breaking things up across addition or pulling constants out front. We've done an awful lot of that at this stage. These properties don't really have like direct analogs to those. So the first one is another property in the vein of, did Professor Carroll write something wrong? I didn't. In this instance, you'll notice I usually use B for my upper limit of integration and A for the lower. The roles are reversed here. You can think of this in some senses like if you were having to try to travel backwards. Like if you imagine B and A on the number line where we have, it's like we're going from here to here and we're sort of moving in reverse. And that kind of gives you an idea as to where this is going. So as it turns out, if we flip-flop those limits of integration, if we walk backwards, it hopefully makes sense from a mathematical standpoint that kind of, amounts to having to negate something. So it turns out that the definite integral of f of x as we go from b to a would be the opposite, the negative of our standard integral of f of x from a to b. So that's one of these 2 properties. I said it's kind of hard to draw a picture to represent what's going on apart from you. Imagine that you're going backwards and sort of undoing stuff. Maybe a negative makes sense there. Property 5 does have a pretty clear geometric interpretation. I generally refer to this as what I call the splitting property. So anyway, so you'll see what that means in just a sec. And so I'll go ahead and write it up, and then we'll talk about the setup. So we're splitting a definite integral up into 2 separate definite integrals, which we did that with the sum and difference stuff before as well. But this time around, I'm actually changing my limits of integration. You'll notice I've kind of inserted another number c here. So if you want to see like a picture of this thing in action, one more time. It's scary how quickly I can produce that, right? So imagine we've got some number c living between a and b. So if I were wanting to measure the entire area from a to b, hopefully it stands to reason, assuming I actually hit the b tick mark appropriately, I could measure this area first, measure the area right here second, and then combine my results via addition. That's exactly what this is telling us if you remember that definite integral is area analog. So we've already technically used this property without actually mentioning it. Again, this part can be kind of intuitive. When we were talking about those triangles in our very first video on this stuff, we were technically using this property. I was using those points where we would transition from one triangle to another, working out what's happening individually over each piece. It's the same principle. The weird part about the splitting property is that it still technically works even if c doesn't live inside here. So long as your function f of x stays defined, c can actually live over here as well, and that's sort of where that walking backwards bit will come back in. Let's take a look at some examples, and hopefully this will end up making some sense. So pause. There we go. All right. So again, assume we have gone to a lot of pain. We've set some graduate students or something to work on finding values of definite integrals for some functions over certain x ranges. So this time around, you're going to notice the function on the interior stays the same. It's the limits of integration that keep swapping around in this instance. So we got that guy. From -1 to 1, his value is 3. From 1 to 3, he has a value of 5. And then from 2 to 3, the value of the definite integral is -2. So somebody worked really, really hard to come up with these numbers. So now it turns out we had our ranges wrong. We need to work with something else. And it turns out we want to know what f of x is doing in terms of area, definite integral, potato, potato, from -1 to 3. We haven't done this. Despair! We're going to have to work more. I mean, we are anyway, but it's not quite as bad as you might think. So, we want to know what's happening from -1 to 3. Well, this tells us what's happening from -1 to 1. That's good. Then we've got something that tells us what's happening from 1 the rest of the way out to 3. So, invoking that splitting property. So, I'm going to use 1 as my splitting point, if you want to put it that way. So I've got what's happening from -1 to 1. We know that. What's happening from 1 to 3. We know that too. So this guy had a value of 3. This guy here had a value of 5. And our overall definite integral for f of x from -1 to 3 would have a value of 8. So, phew, that could have been a lot worse if we'd had to go back to the drawing board. Unfortunately, it turns out apparently we were wrong again. We actually didn't need quite this much. So our boss, research advisor, calculus professor, whomever, tells us we want to know what's happening from -1 to 2. Well, crap. We look at this, we only actually even see the number 2 appearing as a limit of integration. One of these things, that could be kind of, unfortunate. Here's where that weird way of using the splitting property works. Based on what we've got going on, we can tell this thing is defined all the way out to 3. So we're going to use that splitting. We are splitting at 3. Again, that feels really weird because it's not between these two, but it works. So again, keep in mind, whatever value you use is the splitter. That's not a technical term. Don't go looking for it in math textbooks. But it needs to be sort of an opposite roles in each of these two definite integrals we construct. And we just worked out this guy, right? From -1 to 3, we figured out that had a value of 8, right? Okay, that's promising. This one, though, we still don't really know what's happening from 3 to 2. 3 to 2 sounds really goofy. Wait a second. We can use that property 4, the walking backwards one, because we know what's happening from 2 to 3. We've got this -2 here, so all we need to do is negate it. So this value we came up with in the last example, it was 8. This one, that, as you said, property 4, the negation property, if we flip-flop the order of our limits of integration, we get a negative of this thing. My apologies for the nested parentheses, but we have 8 plus -2, negative of a negative, it's a positive, yay! So then we just get 8 plus 2, and our overall integral has a value of 10. Whew. I was getting really worried there that I was actually going to have to explain how we might have to come up with one of these things. We're going to do that, but that's the content of our next section of material, so buckle up. I love you guys.